Okay, this video is in addition to the previous one, to the video where I talked 5 hours long about basic trigonometry with a portion of basic geometry. The thing is, there I said that you can prove yourself that through 3 points that are not collinear, we have a unique circle going. And I got kind of interested in it because I didn't want at any cost, I just didn't want to really prove it solving the equations for those points. And so I wanted to come up with other solution, and so I did it, and I'd like to show you some things about it. Because well, yeah, just to fill this gap in the previous video. Right, because well, I actually haven't shown that through 3 points there is only one circle, and I'm always insisting on videos being self-sufficient, right? Okay, so I also wasn't sure for a moment there if it is even true that through 3 points we have only one circle. Now I have the answer because I have come up with something, and that's actually really simple. I thought we have to solve those equations, but no. If we would have had to solve them, I don't even know if I would make that video. But okay, everything in the new order. 3 points, one circle. Okay. We take a setting our xy plane, as always, if you like, with Cartesian coordinates, xy plane or R2. All right. That is just, so to speak, the x-axis squared. There's y-axis, there's x-axis, and we square the x-axis, which are the real numbers, right? Because y-axis is same thing, only in another direction. Okay, but well, square is of course in sense of Cartesian product. So what do I mean by that? That Cartesian coordinates are basically are actually exactly elements of the Cartesian product. So it's not a coincidence that in both cases we have Cartesian there. Right, but well, given 3 points A, B, C in R2, and we call their coordinates in R2 the x coordinates, y, 2, by b, b1, b2, and so on. C1, C2. And our task is check if there exists a circle on which A, B, C lie. Check if that is the case. If the circle is unique. Okay, first approach. First approach. Try to fit general circle equation and are true to the points. That is, we are trying to choose the parameters of a circle equation in the way so that the 3 points lie on the circle defined by this equation. Try to fit general circle equation in our true to the points. Oh, we call the general circle equation. We have a middle point of a circle, and let's call it xy, right, without thinking much. And we have the radius. So the parameters are the coordinate x, the coordinate y, coordinates of the middle point, and the parameter radius of the circle, right? And the general circle equation is, of course, well, what do we have? We have that the distance of this c to any point here, this is the points in the circle, so I'll call those points, I don't know, something like, okay, let's do it like that. First, do it in a self-suggestive way, right? Distance of xy and p is equal r, right? Here, I haven't defined it yet, but it is just the correspondence to our visual intuition. A circle is defined by its central point xy, and the distance to any point should be r. So such a circle would be defined as all points p satisfying that and exactly those constitute the circle with middle point c equal xy and radius r. All right. All right, and this is just the description of the points that lie in the circle, and visually it is clear, it is exactly the point. What dist means, it just for now the visual distance, we will discuss it in a second what it really is, but for now it is just the visual distance of the central point to the point in question, and this visual distance should be equal to r. So that is exactly how we imagine a circle. That is exactly the points on the circle, that is those points on the circumference, right, are described as all points p satisfying that their distance to the supposed central point is the radius, and exactly those. So that is all points that satisfy this are certainly on the circle, and it is exactly those, that is, no other points are on this circle, and that is an important distinction. All points satisfying that, and exactly those. In mathematics, we usually think that automatically, but I'll say that here explicitly. There are different ways to formulate it, And exactly those constitute the circle with middle point C equal to xy and radius r. So exactly the points here. Right. Right. And well, now let's talk about the gist thing. Well, what do we have to measure? We have to measure this line, right? And we have that point xy having its coordinates, and we have that point P having its coordinates. Right. Okay. And we want to measure this thing. Well, we could think of something, right? This is something familiar. It kind of asks for us to draw a familiar shape. What shape? Well, we just draw those line segments that will make out of it a right-angled triangle with this hypotenuse. How do we do that precisely? How do we describe that thing? Well, don't forget that we can use the Cartesian coordinates if we like. And for them, orthogonality is defined axiomatically. Then this, from this point P, is drawn exactly parallel to x-axis. This is just a line drawn parallel to y-axis, I mean, from your point P downwards to the y-axis, and this parallel to x-axis from the point xy, and this is just a line, and those lines intersect in a single point, and this will be the third point of our triangle. Right. By the way, maybe it's worth mentioning, in serious mathematics, the place of axioms will take definitions. It's kind of like it's a silent transition. We just define the objects in a way that they make sense to satisfy what we want. Of course, so with requirements of minimality, the object has to be defined in with the minimum amount information possible. But yeah, other than that, axioms become definitions. But I won't go into it on that level. We just have that it's an axiom that those are orthogonal, and then we can construct those parallelly, and then we have this intersection point, right? And now we can use, just to compute this distance, we compute it completely consistently with what we learned from Pythagorean theorem. The distance will be exactly, if we translate this triangle and think of it in terms of the planar distances, of course, this distance would have to be computable by Pythagorean theorem, just because if we want to have triangles consistent with dealing with vectors, then it has to be the case, right? And well, how do we compute that? Well, we just recall what is actually the meaning of a coordinate, and that just means if that is the x-axis here, right? Then the projection of this point here has this distance from a zero. Here's x-axis, here's x-axis continued, and here's our coordinate x, and here's our coordinate p1. P1. And then this is, of course, P1 minus X, because this has distance from 0, P1, this has distance from 0, X, and then we have P1 minus X being this, let's call it B. This leg of the triangle is called B, right? Same game here, Y projections, and we have then coordinate Y, and we have coordinate P2, and we have, well, let's put it like that, so that you have everything in your familiar environment, and we have P2. Here you point P, right? P2. We play the same game with the y coordinate and get that. And then the Pythagorean theorem just gives us that this distance, if we want consistency of abstract geometry in an abstract plane with the coordinate plane, we just have to have that by Pythagorean theorem. C is P1 minus x squared plus P2 minus 1 squared. And this is also what we call the distance of those points of the square root here. And we denote this distance, actually, there is a special notation. Also called Euclidean distance, most natural distance to take in the plane. All right, so we just have that P, we have that XY, where P and XY could be any points in the plane. You could do same construction, doesn't matter, right? And we denote that, which we have defined now, the distance. This is, by the way, distance is defined as C, and C is computed like this, right? And distance is defined as C, and we define that thing after we have defined the distance as C for such 2 points, right? We define that just to be denoted, it's just notation, right? Pi minus xy, but xy is C, and so we do it customarily. We give those points as name, and this is called Euclidean norm. So Euclidean norm, if you hear that that term, that's just this most natural distance between the points computed by the Pythagorean theorem. And of course, it is generalized to higher dimensions, same using Pythagorean theorem multiple times, but does not interest us now. What is interesting, we now have the natural and very neat definition of the circle, because R is just supposed to be this Euclidean distance. With much plausibility, right? Okay, and well, now I will write our circle properly. For circle with middle point xy or C, and the radius r, we just write CR CR, and this all points satisfying that, and exactly those we write in the set notation. You might be not familiar with sets, but that just means that. That's all points that satisfy that, right? And in informal terms, we write distance, well, that this has to be, okay, I called that C, so C equal xy. I can use that interchangeably because I just say that the coordinates of point C are called xy, so here distance of C to P is equal R, but now we know what distance actually means. And in the set notation, we get that those are exactly those points that have the distance to C, Euclidean distance equal to R. And the Euclidean distance is just the most natural distance. Simply exactly measure this distance by a ruler, and you just get same if you compute it by the definition of this. So this is most natural thing, right? This defines circle, and this is the general circle equation. All right, but then now recall what we wanted. We wanted to fit this general circle equation to the points A, B, C. What does that mean? Well, to the point to satisfy this equation, it has to satisfy this. So now fit the equation to ABC and recall what our aim is. Our aim is to find the circle that contains the 3 points. And if there is one, then to show that it is unique, or maybe to disprove that it is unique and to find two circles if we are wrong. Now fit the equation SIR, which is given in general form. That could be any point C in the plane, that could be any radius, to ABC. And what does that mean? Well, those points lie in the circle if and only if those points satisfy this equation, because this is just visually, this is that we can interpret that is kind of an axiom, but this is kind of what we see. What our axiom is, what we see really works in conceptual terms, right? So it is reasonable definition of a circle because it is kind of what we see, but we could also say we'd like to define a circle in exactly that way, right? And what we see, well, circle goes to this when the points satisfy this equation. Right, and fit the equation to them then means that we have a system of nonlinear equations A minus C, and we don't know what is C and what is R. It could be any circle, but if there is one, then it satisfies this. And if a circle satisfies this, then yeah, then there is one. If we found a circle that is satisfying this, then this circle works. Right, but C and R are now unknown. I shouldn't call this point C, by the way. Or let's call this point D. Let's call this point D. And then I have also the corrected above, and we have that system of equations, but of course it's kind of handy to work with that. So let's write that out. D, D1, D2, A, B, D. All right. Into the middle point of the circle C, and we write that out, and we remember this definition, right? So written out, it reads like A1 minus, okay, I called it X. So plus 2. There's just this definition written out, right? And the squares allow to interchange the order, so I won't care about that. Probably I will obey the order anyway, but well, just so you know that it doesn't matter, right? You have to keep attention. You have to pay attention to what matters and what not, what stays equal. Okay. I don't, because I do it automatically. Okay, oh, I will correct myself if I do a mistake there, but that's very unlikely. Okay, d1 minus x plus. I just have written out the definition, right, that we have given just now. We have realized it is the proper definition. And now we have that equation. For some unknown circle with those central coordinates of the middle point, xy, and this radius r. And now we could solve that, but well, we could just square this and you get this, and then you would have to square that, and like you would have to express that with that. We don't like the perspective of solving this. At least I wouldn't like that. So I found another approach. At least in my mind it worked. If it really works, we'll see. And also, don't forget that, well, I didn't want to spoil the result, but for some points there would be no circle, and we will see it now very explicitly. What I thought then about was, wow, why don't I give a geometric solution to that? And I came up with the following second approach. So you could solve this, of course. You could solve this and consider cases when it is solvable, when it is unsolvable, and things like that. So I don't like this. By the way, of course, I'd like to have. This is just our assumption. Distinct points. Our rest is just, well, we could consider that, but well, this is just our assumption. I don't want to go into the formalism. We could also have a general form where they are not distinct, but well, it's just I mean, really a general form, a general equation, but I don't want to do that, at least now, at least not in the school maths videos. Okay, second approach, the geometric one. First, no, not first, just consider a circle. I know we want a circle, we have the points, but we now just consider a circle to learn something about properties of points on that. And you'll see why we do that. Consider a circle as a geometric object. If we have any 2 points in the circle, you can pick what points you want to have, like any 2 points. Right, like any 2 points, whatever. Right. Then you will always have, just by the definition of a circle, no matter if geometric or algebraic one like above, always have that they have same distance to the origin. And I claim that that means that the middle point of the circle always lies, for any 2 points on the circle, the middle point on the circle always lies on the line that halves the line segment connecting those points. And how do we prove that? Well, we just take any 2 points in our plane, any 2 points, prove and we prove the following. The set, and you remember the notion of the set from above, it's exactly the points that do that. The set of points having same distance that's different A and B, by the way. It's just another A and B, another setting. Oh, okay, not necessarily, but it is just another consideration. You should not get confused, and you should get used to it that in mathematics it is important to keep in mind the context. So I will do it with just same names for some points that could be points. A and B from above could be different points. The set of points having same distance from A and B, also called equidistant to A and B. Is given as the line. Do you remember those points? It's exactly those points. As the line orthogonally halving. So dividing into halves, orthogonally halving this segment AB. How do we prove this? Well, a point that is equidistant to them. What should it satisfy? Well, let's see. You recall distance from above, right? First, we'd like to show that all of those points, oh, well, no, let's show everything at once, that all those points are on the line, and that this line is exactly the right line, right? How do we do that? Well, let this be some point that does it, right? And just investigate what this point does. Again, C is just some point having same distance. I'm already drawing it on the line, but for now you could imagine that the C is also here. And we claim, well, that's kind of same distance, because it's not the drawing that matters, but what matters are the relationships. And we'll see what we will get from that. Okay. That is supposed to be equal. And of course, A and B are distinct again, but okay, that's pretty obvious, right? Point having distance to same from points having same distance from same point and same point. Oh, that's the whole plane. Yeah, the whole plane. Okay. 2 plus C2 minus B2. And this should be equal, and that means that is equal if and only if. And this is indeed a positive number, so we can actually can square not necessarily. Well, if we square right, if we square, that direction works, and the squared thing is positive, so that direction also works, right? So that direction works. We can, if we have that, we can square and have equality, and if we have equality, we can have the square, right? Because that both is positive, right? All right, so we square, of course. Okay, and we have some equations for C1, C2. And of course, you see that is a line, so one parameter has to be free parameter. We have one equation, we have two parameters, C1, C2, A1, A2, B1, B2 are given because it's just given points, right? And we have to solve it for one of the parameters to just see that the form of such points is line given in a dependence on coordinates, given with fixed coordinates A1, A2, B1, B2 as constants in some way of dependence, right? But let's look at that. Plus C2 squared minus 2C2 A2 plus C2 squared is equal. Okay, that's quite tedious, but okay. Oh, yeah. As we expect, the equation is linear. That's already good news. I don't know if you can see it already, but the square terms will be eliminated, just like we'd like it to, because we'd like to be relation just linear, right? That's what we wanted. And that it really gives the line that we'd like to have, that we will have to look at. And I didn't know if I will consider that in school terms, in school, in the language of school notions, because it would be tedious, but okay, let's see, maybe. Minus 2, C2, B2, plus B2, 2. Right, on both sides we have C1, C2, and that's not elimination like by fractions, but I subtract on both sides equal terms, and then it stays equal, of course. Right, and nothing else we can somehow eliminate. Okay, everything else stays, and what we have then, just bringing the C1 to one side of it, right? And if I'm bringing C1 to one side of it, then I get bringing that contains C1. Okay, well, I'd like to have what? Okay, without some certain object, I don't like the odds, but okay, well, okay, I'll do it without that. Okay, minus 2a1. Okay, that's one. I don't care about what I said there. It's a nice way to think of that, but well, it's a little bit overkill maybe, so I won't do that. Okay, what we have here is okay, something we can do nonetheless. I can permit myself one thing. You recognize familiar objects here properly, right? You recognize b squared 2 squared. All right, and minus a squared. Okay, have we accounted for all terms? We have accounted for that term. We have accounted for that term. That was here. Right, brought to the other side, change the sign, bracketed that out. Okay. Right, a1 squared is here with the other sign. Okay, b1 squared is here. All right. Then what remains here, that, here, all right, here, that, here, all right, and here, that, here, all right, and what remains here, that, here, that. It seems like that. Okay, and you recognize here something, right? Well, not necessarily. Okay, no, you don't. Okay, you see, okay. How would we do that? Of course, you see that it is a linear relationship of sorts, right? So the point C1, C2 is given as linear relationship. What I mean, if we wanted to express C1 as a function of C2, then the relationship would be linear. because we would have brought that on the other side, we would have divided by that, and we would have obtained that. But I do not quite like that. I'm very much tempted to use a certain notation, but okay, I won't do that. But okay, how do we do that in elementary terms? Okay, well, we'd like to have a line, and for that we actually have to show that this is a line first, and then that it is the right line that we'd like to have. Okay, so well, let's just bring that. That's actually something is weird. Something is weird because I would not think that. Okay. Okay, I kind of do not like that, but okay. Okay, well, what do we do next? Well, we recognize, of course, that this are coordinates of B, these are coordinates of A, and they're kind of distributed among these vectors C1, C2. And there is a nice thing about that, but let's forget about it and just think about it properly. All right. We have that line. Okay. Sorry, I meant we have that something for which we expect for that to be a line. To prove our conjecture, now I would like to use a certain tool, but well, let's do it without it. But so that I have to think. Wow, you see, oh, wait, why am I even thinking about something? Oh, I know. Yes, I have to think because we have to show that actually there is some constant and some vectors so that well, that is even true. I'm wrong. This is not a line. Well, of course it is a line because we have linear relationship between those, and those are just constants. But I'd like to bring it into a form that is more familiar to you, where you constantly say, "Well, that's a line." Here, of course, it is a line because the relationship is linear. Yes, but well, you might be not that happy with that. So let's bring it into the more familiar form. How do we do that? So we'd like to have some slope of that line, and we'd like to have some vector that pinpoints it, right? A line in R2 is that is the pinpoint vector, that is the slope vector. Right. How do you do that? Having that. Well, I don't know it right away, I think. Well, but I can still use. Well, I mean, I would like to use some tools from higher level, so to speak, but okay, let me translate that into language that you understand. Um, I have also to admit that I forgot a little bit myself how it goes, but I would remember it fast using the abstract formalism, but now I'm trying to um, constrain myself not to use it, but to remember that in a elementary fashion, and it just doesn't seem to work well. Well, let's see. The first thing that we could think of that we point. Mm, wait a minute. Does it or does it not? Well, if I would only see this, and I would only know by elementary considerations that it would have to show that it is a line, how would I do that? That's the question. Okay, well, what I would do would actually be really computing this. C2 is equal to B1 squared minus A1 squared. Let's see where it brings us. Because this is what I would do just to get another coordinate. I didn't want to do that. I want to stay on the elementary level, but I didn't want to do that. I wanted to go another way because, wow, it's a lot to write, but let's just do that and see where it brings us. All right. With that, the points that lie on our line are exactly the points C1, C2 with the property C1, and the second coordinate we just take from here, right? We have just for any point that satisfies the relationship of being equidistant from A and B, we got exactly this equation. It was equivalent to being equidistant. And now we have that for any such point, it is equivalent for C2 being in this relationship with C1. And now let's just write it down and see if we get the familiar form of a line that way. Okay, I don't like that, but okay. Well, why not? Okay, well, what we see actually looks pretty much like it, right? C1 is given, and we can now write this just by rules how we deal with vectors, right? Component-wise. And pay attention to what is what, right? And where I have taken what out. Okay, I could have eliminated that right away, D2, but okay, keep it like that. Doesn't matter. Okay, but be cautious. I have first multiplied out that 2, got 2 multiplied by b1 minus a1 in bracket. Here I also multiplied it out, then I eliminated it. So I didn't eliminate in some way like here, 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 here. Here it worked, but generally does not work. So that is what I did here, right? And here just how that works. Right? I just first took that vector out coordinate wise. If we add that to this, what remains here when I take this vector out, then we get exactly that. Just get some exercise in dealing with vectors if you have trouble with that. Simply coordinate wise dealing with vectors. Wow, okay. I have like we can bring to fractions to a common denominator, we can oh, like we can simply calculate the numerator when the fractions are given with the common denominator. We can also do it the other way around. We have common denominator, we have a numerator, we can prove that into two different fractions. And I get that fraction, right? That is a fraction. Here, imagine here is a cut for the fraction line. And I get that fraction, right? And just put it out. And here I have then, I can, here I have 0 plus 1, and here I have that fraction minus that fraction, And I can pull out that into vectors. And in the first vector, I multiply out C1 out of the vector as a constant, right? And well, the second vector is just this, right? And this indeed gives us a line because recall what the line is. Lambda v, or lambda is our C1, v is that vector, and that is that vector. And you can see very clearly that it is a line. Recall our coordinate system, recall our vector w, and w just goes to somewhere, right? And now what does lambda v do? Oh, lambda v just gives a line here, because if you have a vector v and lambda, then it is vectors of scaled length, but in the direction of v. So this is lambda v. And then you just move this line to this position. So the final line is that one, right? And that is certainly a line because you have that structure and then you move it, right? And here you have exactly this structure with this vector, and this constant. Right, so all right. And here, of course, it does not have to be orthogonal. It is just moving this line to some new position, W. Right? And that characterizes a line. So indeed, that is a line. So okay, but that it is a line is not enough. We wanted more. All right. Let's look at that. Okay. Those points have that form, and that's a line. That is already great, but the question is now, is that really this line that is orthogonal to the line segment on which A and B lie, and that halves this segment. Well, to halve this segment, this line simply has to... Okay, let's write it more properly because we don't have it properly here, right? B1 minus B1, B2 minus B2, and here 0, B1 squared minus 2 squared plus B2 squared minus 2 squared. 2. Okay. Yeah, let's take a proper look. First thing, whether this line really contains the middle point of the line segment between the points A and B. And you know how to compute the middle point because you know how to compute distance, and then you know the coordinates. Okay. Or you could simply look at the coordinates and you could see that this has the coordinates, the middle point has the coordinates 1 minus B1. Okay. That is a special case where it is parallel to x-axis. Let's take a more general one. And then you have that it has the coordinates, of course, half of the length taken from one of the points, right, and half of the length. Okay, let's write length and how we know to write it now. And half of the length from this line, this is A, this is B, right? Because of course, you don't have to be points parallel to x-axis. We don't want to restrict it to this case. I mean, points lying on the line parallel to x-axis. Okay, that is this distance, and of course we have to take the coordinates. What I mean, we have to go that on that line to obtain this point, but we are now interested in its coordinates. So what we have to do is to compute those two things, right? But this thing is exactly, if you just look at that and recall that it is a middle point, and that thing is exactly B1 minus A1 half away, right? And you see, if you just compute the distance in from any of those points, right? So first our hypothesis is that this point has those coordinates. Being taken starting at a point A, for example, right? Just one half of that distance, one half of that distance. That kind of makes sense. Is that point slides on that line? The distance is here. Oh, wait, that doesn't make much sense actually. I'm now thinking if it really works. Of course it works. Haha. Okay, well, that is a 2. Okay. And if we take now the distance of that from A, we know we have to subtract in both coordinates, right? So that distance here from that point should be that, and we should get that, and we should get it from both points if we take those coordinates, right? Then it would work. And our hypothesis that the coordinates are this was just that, well, if it is a middle point and kind of, it seems like the increase here is also just the half increase, and the increase here is half increase. Well, let's just try it out, right? Okay, then a1 is subtracted, a2 is subtracted, and then we take that to the square, and then we take the square root out of this, and we get exactly the distance half. Right, so that works with A. Now B, I could just say we could rewrite the same point as B1, B2, but let's not do that because we are kind of not allowed to say that. That's exactly what we are trying to prove. More or less, okay. Then let's take B1, B2 and see what it gives us. So, would like to prove a1 plus b1 minus a1 divided by 2, a2 plus b2 minus a2 divided by 2, minus a, and taking the distance is exactly 1/2 distance a minus b, right? Because that's what we want. We want this point to be between them both, right? That's what we visually want. And of course, I'd like to have same here. 2 plus b2 minus c2 divided by 2 vector minus b distance should be above equal to this. And that we have already discussed. Well, just look at that. I have subtracted the coordinates of A, right? And what remains? Well, coordinate by subtracted coordinates of A, that remains. And now we have to take what? Well, we have to take that. Let's not write it as a vector because it's just those subtractions. And then we take the one, right? I have subtracted that, and I have to take that squared, exactly with subtraction, but the subtraction of this with the first coordinate is this, and a2 minus a2 2 squared, and then the square root, and then as I said, well, that is applied to this is applied to this, and this gives you b1 minus b squared, b1 minus a1 squared, a2 minus a2 squared, and here you have exactly 2, and this is exactly the distance of A and B, right? Because this is squared in the denominator, and then applied the square root, of course, brought to the common denominator, and this is exactly that distance, so that we have it. It's the distance. Okay. All right. Here it might seem that it is a little bit more interesting because you actually have to compute p1 minus p1, 2 minus p1, that squared. You have the square root of that. A2 plus b2 minus a2, 2 minus b2 squared, the square root of that. And well, that should also give half of the distance. And let's see if it does. Well, 2a1 just bring to the common denominator, right? All right, and then computing everything. And that should come out what we'd like to come out. Then we have, sorry, that's of course squared. And here, otherwise we wouldn't have gotten, let's say, like also 2 plus b2 minus c2 minus 2b2, and that's that, and that's that squared, right? Just brought to the common denominator. And that gives us, of course, just minus b1 and 1. So that calculated together, that's p1, 2 squared. So same thing as we already see, as we wished to have it. Right. And that is indeed 1 half a minus b. So, hypothesis was right, and we obtained that this point has to have this coordinates, or we could express that as this coordinates. As you can guess, if we would have checked that for the point that has b1 b1 minus that, b2 minus that, would be the same, but now we have those coordinates, okay? And this is the point on that thing, and we want that our line halves that line segment between the two, and that means it has to contain this point. And that is what we will check now. Okay, maybe to solve circular equations would be a little task. But well, conceptually, I have reasons to like this path. You'll see that later. All right. So now show that the line L equal to, now let's replace C1 by lambda because it's anyway C1 was chosen arbitrarily. So we could also keep C1 if you feel more comfortable with that, and just keep C1 and try it just like that. It's no problem at all. And you should understand that it is no problem at all, just from the context in which we are working. So you have to think about it if you have trouble understanding that. Okay, 0. We have that b1 squared minus a1 squared plus b2 squared minus 2 squared, and what's that? Okay, there is a fraction. Okay, 2b2 minus 2a2. 2b2 minus 2a2. That the line contains, and that is, it goes through that point, contains the point which halves the segment AB, which we have identified to be A1. Just one description of that could be A1 plus B1 minus 1, 2, B2 plus B2 minus A2, 2. And what do we have to have with that? Well, we have to have that there is a lambda for which it is satisfied that it gives this point. Well, okay. I'm not liking this very much to look for such lambda. That's why we will return to our. But first, I check the point. A1 plus B1 minus A2 divided by 2. 2 plus B2 minus A2 divided by 2. All right, so that I don't have any dumb typos. Of course, conceptually it seems to be right, but sometimes one just has a block in their head, so better check. But of course, we don't want to like look for lambda that does that. Okay, we go just back to our formulation which we started and we check that. So that has to satisfy this. Right, and now we look at it. And what we observe is, well, okay, I do not observe anything yet. Okay, so check star instead. That is where we started. That is what the points have to satisfy as the condition. But we have shown that it is equivalent to defining this line, so we can use this condition as well. No problem with that, right? All right. Maybe this one. We don't have to do that at all, actually, because we have shown that the distance of this point to this point and that point is same. And we have defined this line to be the line of points of the same distance exactly via this here, right? And this is exactly what we have shown, that the distances are equal. We just have calculated those distances and have shown the same number comes here, okay? Here, one distance, another distance, and we have shown same number comes. So yeah, we have shown it for the point, that's already shown. And the only thing that remains is to show that this line is orthogonal. That this line that we have here is indeed orthogonal to the line segment, right? And well, of course, the easy way, I don't know if you know that, but the easy way would be to do the scalar product of the two direction vectors. Here, the direction vector for the line through A and B would be simple. But I don't know if all of you are familiar with scalar product. This is exactly why I kind of got stuck here, because I didn't want to think of that in terms of scalar product, because yeah, I tried to like ban those thoughts, but yeah, just because I didn't know the school level, I do not necessarily expect you to be familiar with scalar products. So yeah, I mean, to be familiar with what it does and how it works. To be familiar with definition is nothing, of course. We could introduce that right away. We could also introduce its properties, but well, let's keep it really simple without me having too much work. I mean, I would have to introduce that all, of course. So that is why it would be having me having much work. Let's think about For those who know the scalar product, how we could explain that in simple terms, that those lines are actually somehow orthogonal. What is the scalar product? Well, why is the scalar product 0 actually cosine? Oh, for those who don't know, we will work it out now. All right. So now show show that this line L, for which we only know for now that it contains this point, this line L, this is points A and B, and it goes somehow through the middle point, but not necessarily orthogonally, but it's just somehow. So that this line L is orthogonal to the line AB. These 2 points determine the unique line. It is customary just to denote it as orthogonal AB line. To denote the line AB. Right. Right. Just think about the cosinus. Think about the cosinus. Cosinus of that angle alpha. How would we compute the cosinus? Well, we would take the okay, well, haha. Yeah, okay, I see the trouble here. Well, suppose the lines are not orthogonal. Then we could compute the cosinus. I don't want to deal with cosinus in general, triangles. If I have this angle, I can always make a triangle out of this that is orthogonal, right? No problem with that. If it is like that, then of course it would look like that. So no problem with that. Right. And this cosinus would be what? Well, the cosinus of this angle, as we have learned, would be just this piece divided by this, right? So if this line is not orthogonal to this line, then of course we would have adjacent cosinus that is not equal to 0, right? Because cosine is equal to 0. Recall that. That is pi half. Right? It is just the coordinate. If you imagine now the unit circle, you imagine the y line, you imagine the x line, you imagine the coordinate. So that would have a cosinus that is somehow, well, that is not pi half. It could be that we accidentally took this angle, no problem with that, but the cosinus would not be 0. It would be something between -1 and 1 and not equal to 0. How do we compute that? The cosinus of that angle? Well, okay, I also wouldn't like to talk about projections. I would not like to talk about projections. Because there, to be rigorous, we would have to really leave the schoolroom, and well, it's not appropriate for now. That's interesting. How do you show by elementary means that the lines are orthogonal in the plane? I simply don't know any simple way to do that. I would always do it with a scalar product. Okay, well, try to keep it simple, but we'll try to derive this method nonetheless. Okay. Okay, I think I have it. I have it. Okay, 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 okay. You see? Um, we have the middle point, right? And we can use the tangent instead. We use the tangent. All right, if we use the tangent, then we can say just the same. And wait, if that line is then a line that is not orthogonal to this, when the tangent is defined, right? Because the cosinus is not zero, sinus divided by cosinus, everything works, right? And now we assume that this line is like that. So it is not orthogonal to this when the tangent is a defined thing, right? Mm, okay, I think there should be a simpler thing. Um, we just have to show that the only thing that happens if we take this point on the line, which we know to be on the line. Okay, I know. Let's just show. Let's show. Ah, okay, no. No, 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 no. We need orthogonality again. No. Okay, yeah. Let's consider the tangent. Let's take any point on this line, and I mean really any point, and consider the tangent. And consider the tangent of the thing that comes out there. Right. Well, okay, no. Again, it confuses me that I have drawn the points like that, because here it wouldn't be that simpler. I would have to consider tangent again and some projections. So I don't think we can avoid projections at each point. Mm, wait, maybe we can nonetheless. All right, we have that. And that is AB. And we have that line through that. And this line is somehow like that. And well, yes, the thing is, we don't have anything to define orthogonality other than well, other than scalar product and projections. We don't have anything else. Okay. Mm, okay. I'll introduce the scalar product. Definition scalar product. I mean, I would not have to introduce that, but I would have to work with that. Definition scalar product. For two vectors, v1, v2, w1, w2, meta 2, define. This is kind of a thing that where you just write in those brackets with vectors, and this spits out some number that is computed like that, right? This is just an abstract thing. What it is doesn't matter. It just does that. All right. Now we claim makes sense to define orthogonal vectors, and we mean literally, like orthogonal vectors means we can draw those vectors like this. You know that the vector is this is same vector as this is same vector as this. I mean same vector as this, same vector as this, but we can draw them like this. Right? Makes sense to define orthogonal vectors via V is orthogonal to W if and only if this is just shortcut for the coordinate notation schedule. If this is 0. And now we'd like to look at as to why it makes sense. Because otherwise it would be just empty definition. Well, we just go into the unit circle. And here we have all the unit vectors, meaning all vectors in all directions, right? You just their endpoints are just the points in the circle. This is unit circle, and their start points is just origin, right? And we'd like to know when such two vectors are actually orthogonal, right? Well, the cosinus of the angle between them, you see, if you go like that, and of course because of rotational symmetry we can consider just this case where this is this vector, because it would be all the same, only rotated differently. So we would really have all cases here. This vector slice here, the endpoint slice on the circle, and this would be given when the orthogonality would be given when cosinus. So no, let's just look where the orthogonality is given. And the orthogonality is given at this point to this vector, right? I have. It is given by this point, 3 by half. And as you can see, the coordinate y is exactly the points where coordinate y disappears. And it is exactly the points where cosinus alpha is equal 0. It doesn't have to do anything with that yet, right? But it is exactly those points. So what we have, when the vectors are orthogonal, cosinus is 0. And when cosinus is 0, it's exactly those 2 points, the vectors are obviously orthogonal. Just take cosine of 0, and that is we have to go to this point or to this point, and then the vectors are orthogonal. Right? And for orthogonal, we have to have that orthogonality, so it is the same. All right. So that is if and only if. Now, show cosinus alpha is 0 if and only if the scalar product is 0. And W correspond to endpoints in the unit circle. Well, you see, if we have that vector has what coordinates? Well, the coordinates of your point, considered now as coordinates of your vector, and this vector has what coordinates? This vector has coordinates 0, and this vector has coordinates -1, 0. 0, -1, because the second coordinate is -1 here. Right. All right, this is -1. Now consider their scalar product. Okay, I shouldn't write in points. Of course, it doesn't matter, but okay, for you it's kind of does for now. So let's write it like that. And we have defined it as 1 multiplied by 0 plus 0 multiplied by 1, which is 0. And same game here. Of course, the scalar product is symmetric. You can just say that in coordinates. Right? We can also write that like that. And of course, that seems 0. So indeed, the cosine is 0 exactly in those points, and exactly in those points, also the scalar product with this vector is 0. And you can also see that it is exactly, for now, we have only that for this vector, it is indeed given that in those points that is 0. That is, when the vectors are orthogonal, then we have, when a vector is orthogonal to this, that is here and here, then the scalar product is 0. But now we have to have the other direction to see that it's to say that it is if and only if, that it is given if and only if a vector is orthogonal to this vector in the unit circle, if and only if it is given. We have to exclude all other vectors to leave only this, right? So let's take another vector to show. Take a vector on the unit circle, that is the endpoint is on the unit circle. Not equal to 0, 1, or 0, -1. All right, but of course that vector has to be on the unit circle. How do we do that? Well, you can guess, you recall just what the points on the unit circle are according to their coordinates are, and they are just cosinus alpha, sinus alpha, with alpha. The points are exactly in that notion, in that shape, and of course it corresponds to what we'd like to have, that the distance is 1. Well, just take cosinus alpha minus 0. We take now the distance to the middle point 0 plus sinus alpha minus 0 is equal 1, as we know we have shown it by Pythagorean theorem, right? So indeed, this is exactly the vectors on the unit circle. And now, if we have to show that if we take such a vector, and the scalar product turns out to be 0 with this vector, then already cosinus alpha was 0. Then already it is one of the vectors 0, 1 or 0, minus 1. All right, then take our vector 1, 0. That is this test vector, right? And take the scalar product and see what comes out. Cosinus alpha, sinus alpha is equal in scalar product of cosinus alpha, because we have cosinus alpha multiplied by 1, 0 multiplied by sinus alpha. All right, the scalar product is equal cosinus alpha. And that shows, and the cosinus alpha, as we said, was 0 exactly as those 2 points. That is, if we don't have those 2 points, then we have that this product, this scalar product, is indeed not equal to 0. So this shows that. We have shown, of course, there was a shorter way, but as I told you, I'm doing it spontaneously. So we have shown the equivalence of having scalar product with that vector for a vector in a unit circle. Having scalar product 0 with this vector is equivalent to being one of those points. But being one of those points on the unit circle is equivalent to having cosinus alpha equal to 0. And so everything is equivalent, and having scalar product at least to this vector in the setting of the unit circle is indeed equivalent to cosinus alpha is equal to 0. But now we have rotational symmetry. And in higher serious mathematics, that is expressed by invariance under certain orthogonal transformation, but we don't need that. If you know that, yes, that's that. Now we have rotational symmetry of R2. And what else? Size symmetry. That is, you can enlarge one vector or another vector in the geometric configuration of how they're positioned doesn't change. And with that, we have shown for all vectors 3W in R2, points or vectors, because two coordinates we can identify them, right? All right, and with that, the only thing that remains, as you can guess, the reasonable thing for lines to be orthogonal, if we have orthogonal lines in R2, that just means we take any vectors in them and look if they are orthogonal on them, meaning that is the vectors giving the direction of the lines. So in that, it would be this. We have to check orthogonality of these vectors. Right, makes sense, right? The lines are orthogonal if such vectors taken in any way but along the line are orthogonal. All right, And of course, this has a much more rigorous formulation. That seems like possible, yes, but it is not a valid, not a quite valid proof, especially that here in higher mathematics it is replaced by application of a certain object called orthogonal transformation. We don't do that now, but yeah, it was an argument of how it works and why it works. Right, and now finally we can look at our line. Let's okay. Let's look. Let's compute the scalar product of direction vector of L and of AB. So we take direction vectors. That is exactly those vectors, right? Okay, vectors that give that. Right. For that, of course, we need direction vector of AB. Well, that's simple. If we want to go from that point to that point, and that is AB, of course, such a direction vector could be given in such coordinates. B1 minus 1. Just imagine that's the origin, because it doesn't matter, right? It could be that, but this is we are only interested in directions, so AB, A2 to B, that same vector. Okay, it might be not drawn the same, but same vector, right? B2 minus A2 is the vector which we have to take the scalar product with the direction vector of that, and that is that one B1 minus A1, B2 minus A2. 1 B1 minus A1, B2 minus A2. And I think it does not work. That's great. Okay, that's another notation for scalar product, but let's keep our notation that we had. And we have B1 minus A1, scalar product of B1. Great, that doesn't work. Let's see what we did wrong. Well, somewhere something is switched. That's already clear, but where? I don't see that. I don't see that. Ah, okay. Here's a minus missing because we have 2b1 minus 2a1 from here, 2b2, 2a2 from here, but the minus is missing because this minus from this fraction, of course, goes to here, right? All right, that makes sense. Here's a minus. Here is a minus. All right. Here is a minus. All right. Okay. I think. Not here, of course. But here, as I said, we just take this vector, and now it turned out that we had a minus missing here. And I'm not just making it right so that it works. You see, here we had that, and we have put it into two fractions, right? And pulling it into two fractions gives, of course, this with minus. And I have forgotten this minus that was before that, right? And so I have formally collected that. And now it works indeed like we wanted it to. Right, because it has to actually. So it would be funny if it didn't. So I knew if it doesn't, there must be a mistake. I only have to look where. And that is indeed 0, and those are orthogonal. Wow, okay. With that, it is proved that for two given points AB in R2, their equidistant set, this collection of points that are equidistant from them, their equidistant set is the line having the segment between them orthogonally. Right. And well, recall how we proved that, well, first we characterized all such points, and it turned out we did on a line. Then we have seen that this line goes indeed through the middle point of such a segment. Right? For that, we had to compute the middle point, and we have verified that it is the middle point. And we just had that this line contains all such points. So in particular, this line with that equation that we have derived for the points being equidistant from the both points that this point indeed satisfies this equation, because this equation was derived for this context. Points satisfying the equidistance condition from both points. Right, so the line with this equation contains that middle point of the segment. And then we set out to prove the orthogonality of the line with this equation that we derived. And indeed, it was orthogonal. And for that, we had to make a leap to looking at orthogonality and how we can characterize it in R2. Right, and using this characterization, dia the scalar product of the two vectors being 0. I mean, we use the characterization scalar product of the direction vectors of two lines being 0. We derive the direction vectors of the two lines. For AB, it was particularly easy. For our line, we had worked before, and we have looked at the scalar product for directions. It was 0, and with that, it was proved that the line with our equation is exactly the line, and the line with our equation satisfies everything. Right, so we know now that for 2 points, 2 given points in R2, the set of equidistant points of M is exactly the orthogonal line to the line segment between them that goes through the middle of the segment. All right, why did we actually care? Because we made this observation on the circle that it should actually be this line. It kind of seems like that, right? And then we'd like to prove that. Now, the middle of the circle is one of such points for any 2 points on the circle. So if we take points A, B on the circle, on any circle, then we have equal distance to the origin. And then the origin should lie on the line characterized below. So on the line that halves their segment and goes orthogonal to the segment. And this is great because with that, we can now look at the geometric proof of one circle through 3 points that are not collinear. And we can also very easily handle the cases of collinear, not collinear, and whatever. All right, now let A, B, D element are true be given. Consider our circle problem. Case 1, collinear points. That is lying on the same line. Subcase 1, collinear and having same distance and two of them having same distance to the third one. Now we know for every circle, if we take 2 points on the circle, then the middle of the circle should lie on our characterized line that halves the segment orthogonally, the segment between them. So if there would be a circle through them, then it must be satisfied that the middle point of the circle lies on the segment and actually not lies on the segment, lies on the line through the segment. But now there's this point. So this point has to lie on the circle through those 2 points and simultaneously in the middle of the circle. Of course, that is impossible because the middle of the circle never lies on the circumference. Impossible. Okay, we actually don't have to distinguish the subcase, but okay, well, I just thought for a little while. Okay, subcase 2, just collinear. Same game, have that segment, and the middle of the circle has to lie on that line. And this point lies then on the radius of the circle and is neither of the endpoints of the radius from the middle, right? This is the middle point, this is the, okay, I should write it. No matter how we give the letters, right? And this lies on the radius. On the radius from the middle point, because middle point lies somewhere on this line. Okay, sorry. A middle point lies not necessarily here, but middle point of the circle that goes through those 2 points, it lies somewhere on this line, right? So the middle point lies on this line. And the distance from that middle point to this and to this is equal, right? Right. And what you see, if you have a point that lies between them somehow, then this will be shorter than this, Just by Pythagorean theorem, this leg of this right angle triangle stays the same. If we move the hypotenuse, this leg stays the same, right? But this length gets shorter. So if we write here a tilde, b tilde, here we write for the whole thing, we write a, and here b tilde is equal b of that big triangle, right? Then we just get that a squared plus b squared, that is just bigger than any a tilde plus b tilde squared, which means that this is always bigger than this, and well, this is supposed to be a middle point of some circle, right? This is supposed to be a middle point of some circle, so the distance from this point to this middle point and from this point to this middle point, it should be equal, but it can't be, so no circle for collinear points. No circle at all for collinear points. Case 2. 3 non-collinear points. No circle for collinear points. 3 non-collinear points. A, B, G. Then the circle would have to lie on the intersection point of the two lines, of the 3 lines, if that point exists, right? I just took the lines for these 2 points. The middle point of a circle, of any circle that contains them, has to lie on the line characterized by the above characterization that house the segment and is orthogonal to the segment, right? Here I did the same, and here I did the same. This is, by the way, also how you would construct it by the compass. But we don't know yet if those lines intersect. Maybe we don't. Maybe we just do not. Who knows? So if we want our circle, then we would have to show that those lines, those 3 lines, actually intersect in one point. 2 lines always intersect if they are not parallel, and they are not parallel because those lines are not parallel and those are intersecting those lines, right? That has to be proved actually, but it might be also axiomatic. It might be equivalent to the Euclid's parallel postulate again. Not sure yet. But the interesting part is we have to show that those 3 lines intersect. But of course, for that we would also have to show that those 2 lines intersect first, that they are not somehow parallel. Well, yeah, okay, for non-collinear points we can show that. That's not axiomatic. Okay, that's not axiomatic. We can show this. And well, we just have to show that there is an intersection point of those 3 lines, characterized by what we have. And let's call those lines L, not just AB, but L, AB, L, BD, and L, AD. And the formulas for them we already have, right? So it was not for nothing that we have derived that here. It was not for nothing. We can now use it. All right, the formulas for the lines are those here. Right, so That was one formula. That was another formula. They just have to think about how to. Oh, actually, that is symmetric, so it doesn't matter how I do that. I just have to keep that in right places, in right. Okay, let's take, of course, that form. That from here. Right, that is the line L. And now we have three lines. And we have to show that they intersect. Right. All right. 1 minus B1 minus A1, B2 minus A2. Right. Well, L, A, B is just same stuff. And that is the line lambda 1 B1 minus A1, B2 minus A2. And here we have some 0 and we could, by the way, also try to give a geometric proof, but well, this is straightforward. But we could think about a geometric proof. I don't think it would be too difficult to show that those lines intersect, but we could think also about a geometric proof. B1 squared minus C1 squared plus B2 squared minus C2 squared. B1 squared B1 squared minus C1 squared plus B2 squared minus C2 squared. And here 2, 2. And what exactly 2B2 minus 2A2? Okay, B1 squared minus A1 squared plus B2 squared minus A2 squared. And then 2B2 minus 2A2. Right. 2B2 minus 2A2. Okay, I think we got that right. And now BG, well, we just have to write down same thing. LBD is, of course, that's a set, so we have to have four lambdas in R, right? I just write all points where lambda could be inserted anything at all points of such form. This is the set notation here. All right, here lambda, okay, I write lambda tilde. Do not confuse you, that is the same. Here, of course, not that. We just take our characterizing formula now for our point, right? So what I do is just B2 minus D2, that is again B, nothing new, plus 0 B1 squared minus D1 squared plus B2 squared minus D2 squared. And here 2 B2 minus 2 D2. And here again lambda tilde and R and LAD. By the way, this method has an advantage over the geometric one. Of course, we could construct that with compass. That is, by the way, another thing. I already mentioned that, but we could really easily construct that by the compass because we would just construct the lines that half that segment, respectively, and we would just draw those lines and have the intersection point, and with that we would have constructed the circle, right? By the way, that would be also the circle construction for the circle that simply by definition that is has same distance from that, as from that, as from that. That would be the circle that in which this triangle is inscribed, right? All right. So and that would be lambda hat and that would be AD. Okay, then we just have to replace B B things by A things, right? T2 plus 0. And you see, you should appreciate it, the universality of mathematics. I just have to replace that now in the formula, but the formula we have derived explicitly for all such points. It is very, very general in that regard. Of course, it's a trivial thing that it is like that, but you should take time to appreciate it sometimes, to just understand what it actually means, this kind of generality. Right, okay, A2, 2A2, G2, and that is lambda hat in R. Right, we have to find intersection points of those. One intersection point that everywhere we're there. Right, okay. Obviously, that we have just to find the values of. Oh, just is not necessarily the right word for that because it doesn't, it looks like a hassle. I admit it looks like a hassle. We will have to find the values of lambdas so that what results actually is same point, right? And that would give us, well, theoretically, that would give us a system of linear equations, but I'm not that fond of doing that in that case. Well, we'll see. Maybe we do it after all. Well, okay. I would like to have intersection point. And that would be the point that satisfies all those three equations at once. Right. And as it is given here, we actually see something immediately. The O have to be equal. That is how we derive that. You see, if we set a point that should be equal here, 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 then its first coordinate, its x coordinate, should be equal to lambda, should be equal to lambda tilde, should be equal to lambda hat. This is just how our particular shape of this line, what the particular shape of our line looks like. But of course, it's a big advantage. So we are lucky there, right? Lambda, and we could just look at the first ones, LAB. Let's call that that point X is in LAB and is in LBD. We could just consider the first intersection. And we would just have that we have to take this vector and to put that like that. But you see, we compare the first coordinate, as I said, and we have already lambda is equal to lambda tilde, if that point even exists. And what do we do next? Well, we just plug in that equal to that, and we look at what comes, right? If lambda is equal to lambda tilde, then for the second coordinate, we have the equation for lambda already. So we don't have to solve any linear systems. It's very simple here. I'm just plugging in that in LAB, right? Just plugging in that. Actually, not plugging in. I'm simply taking the second coordinate, right? B1 squared minus C1 squared plus B2 squared minus A2 squared 2b2 minus 2a2. Great. And that is that. And LBD. Well, we said lambda is equal lambda tilde if we want a point that is equal on that line and equal on that line, then it has satisfied to satisfy two equations at once, having some coordinates x and y, and it has fixed coordinates, and x is equal to the first coordinate of a supposed point on this line that is equal to lambda if you look at the first coordinate of a supposed point on this line, and x is equal to lambda tilde simultaneously because it has also to lie here, right? And that, and for y, same thing, and we know from x already what that lambda is equal to lambda tilde, and we can then plug in here lambda, right? And that gives lambda 1 minus d1 b2 minus d2. In that case, well, same thing, but now for this. Plus b2 d2 squared 2 b2 minus 2 d2. Well, and now we can just compute the lambda, right? And this is just equality for the second coordinate, and for the second coordinate we already obtained the lambda. And that gives you, well, that gives you, I'm already bringing it on the other side and computing it. You can compute it step by step if you like. Of course, I won't do that because it's just, there's not much point in doing that. I want to show you interesting stuff. But of course, I show you the result of computation, meaning that I will compute it, only that I'll do many steps at once. Minus p1. Okay, no, I won't do that because I actually have to multiply properly, so I will in a way do it step by step because I can't do that, and I could probably, but okay, I'll do it step by step, more or less, of course skipping some steps, but oh, you can calculate it yourself and you'll get the same thing. You should, if I want to do stupid things here, b1 minus d1 2. Let's not do that. We have shortcuts for that. Look at this. This is b1 squared plus b2 squared. What is b1 squared plus b2 squared? Right? Just subtracting 0. And this distance squared, right? If we would have this distance, we would have square root here, but here this distance squared, and we can conveniently just define it like that. Because if it is distance to 0, well, then we just think of 0 here, right? All right, so we can shorten this by this, and you can see here same with A, here same B, here same D, and it's just to write a little less stuff, right? So I'm not doing anything spectacular. just to write a little less stuff. I don't even know if it is a good idea, but we'll see. For now, just write a little less stuff. Maybe we'll have uh, to multiply it all out anyway in the end. But well, let's see. All right, and now I'm just computing lambda, which is same as lambda tilde, if you recall. And that's just, if I subtract that part from that part, I bring that to this, and then I get here b1 minus a1. I bring this to this, and I bring this to this, so I eliminate after lambda, right? And then you get minus b1 plus b1. Okay, what am I doing? Okay, here we also don't have simple calculation. We have to actually achieve a common denominator, and for that, of course, we would have to work as usual. For that, we would have to have b1 minus a1, b2 minus d2. Right, brought to be common denominator here, and also here, and then brought it on the other side. Or shall I brought it on the other side? Doesn't matter, right? b2 minus a2, b1 minus d1. Alright, that's that, and here b2 minus d2, b2 minus a2. Right. That's what we have here. And on the other side, we have, let's maybe just leave it like that for a second. Okay, I brought that to this, and I brought that, and I bringing this to this, right? Right, which gives me 2 b2 minus b2 b squared plus, no, minus, just making the common denominator again, right? 2, 2. And I actually had to b2 d2, I had to take a minus from here, right? And I'm having plus here. I brought that to this side. I brought that to this side. Alright, right, right, right. And I already had that, and I have to adjust that to have common denominator having that. Oh, yeah. Oh, wow. Okay, well, we can actually do a little stuff with that, but let's wait a little bit. For cancel 2 b2 minus d2. Right, now first thing we notice, that cancels on both sides, right? Another thing we notice, we do cancel. ds2. Right, and well, now we have to divide by that, right? But dividing by that gives lambda equal to Okay, that's not nice at all, actually. Ha 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 ha. That's not nice at all. This formula is, man, but okay, we didn't actually expect a nice formula in that case. Oh, I'm rotating around G2 and B2 here to compensate for the minus, right? And I eliminate the minus. Okay. But well, the true problems will begin, and we will try to fit it to the third point. And I didn't know if I will do that because I did not expect such a mess. So of course, we would not have expected a nice formula for that point because it is some point in the middle of nowhere. Okay, that too belongs to this here, right? So here is already a 2 waiting for us. And here we have that whole thing. b1 minus c1 b2 minus d2 minus b2 minus c2. I could have eliminated the minus again, but see no point. Right, maybe it is somehow something decent. Well, some things get eliminated at least. If we multiply them out, some things get eliminated indeed. And that is b1 minus c1, b2 minus d2, b2 minus d2, b1 minus d1. Right, but this calculation doesn't seem that that enticing to me. So, well, I thought that we could do that, but we cannot, obviously. Huh. Okay. Now I don't like that at all. So we got our lambda, right? But now we'd actually have to show that this gives some point with that here. And well, I mean that this point that we have derived here with that lambda, if that with that lambda multiplied by that, for example, this derives a point that is on here with some lambda. So that lambda multiplied, this lambda multiplied by that, of course in first coordinate is trivial, but that this here would give same, we would have the fun of looking at that here. Yeah, all right. Well, here even I would say we would have better calculated with circle equation because, well, it's a pain. Okay, we could have done it differently. Let's look for different approaches. Well, you see, actually we have those three lines, right? And um, we could just find a point that satisfies all those, and that would be a point with, well, well, no, there's a problem. Haha, okay. Hmm. For some reason, that all would have to be the same. Hmm. And it is for same lambda. So for same lambda, we would have that. Hmm. Okay, that calculation doesn't look that bright. Of course, we could now eliminate that, for example, and we would have to. Okay, let's do that because, well, okay, why not? Why not? We would be left in less trouble if we eliminate that at least. Because not much less, but oh, at least something, right? D2. Ah, alright. We don't have to. Ah, yes, we have to. Alright, we have to. You'll see in a second what I'm trying to do. Of course, I'm eliminating that with P2 because it's eliminated, right? This is same as here, so it is eliminated. Right, and then we could say that we have P2, A2. Ah, no, we could not. Ah, yes, we could. D2 is multiplied with that. Minus E2 is multiplied with that. Right, and well, but for that, for B2, we could eliminate that. We could eliminate that here. And we would then have just B2 minus B2 or plus B2 plus B2 A2. All right. I have just eliminated that part. If we multiply it out and multiply that out, and this product is eliminated with that product, right? Just plus minus same thing. Right, and minus d. Okay, well, at least we have some kind of symmetry here. The three parts participate all, right? So it's kind of nice in that sense, but well, yeah. D2 is taken from here, from that. B2 comes here with that, and B2 comes there with that, and minus A2 is taken from here with that. Right, so it's indeed exactly this. And also down here, we have B1, B2 is eliminated, and basically that's it. B1, B2 is eliminated, and that's it, nothing else. All right, that's just great, right? B1 minus B1, D2 minus A1, B2 minus D2 plus B1, B2 plus B2 D1, and here minus A2 B1 minus. Right, and nothing here gives any hope for something decent, obviously. The question that remains is, okay, we found that lambda via this and this. And now this is our lambda. That is, to have that this is on the third line, we would have to actually multiply that by that, and that would give something. And what that would give should be same as lambda multiplied by that by the first line, for example. And well, this kind of doesn't seem that enticing, to be honest. Does not at all. I mean, okay, we could write it in terms of scalar product, and it's, oh, then it looks better. I mean, it's still a mess, but okay, let's write it in terms of scalar product again, just to have some expressions that take less space for no other purpose. But I already see that I probably won't finish this calculation because it's just too annoying. You could do that, but at that point I would say, okay, here you can use calculator, or well, whatever. Here you can use a computer program to calculate that. Computer program that is able to calculate the abstract expressions. There are some indeed. But at this point, it just doesn't, it just isn't fun anymore. It's just calculation. So what you would basically have, just, oh, no. No, no, no. It's not even scalar products. Okay, it's scalar products of reverse vectors somehow. Well, okay. Yeah. Now, it becomes completely unthankful. What we would have to do, or what we could do, would be following. The only thing that determines that the point is the same is lambda, right? So that if that works with same lambda for the third line, I mean, the year we had that if the point lies on the first two lines, then the lambdas are equal. And from that, we have computed lambda, right? And we have computed lambda so that it really lies then on the first two lines, because it was just such an equation like that. Looked very neat in the beginning, right? It was just such an equation. By the way, how did I? Ah, okay, yes. Yes, it was such an equation. And then we had some lambda that does that, and that was already equivalent. There was no problem with that. And we have computed a lambda that does that. So indeed, and of course, we were able to do so because those lines intersect, right? Now, we'd like to show those two lines intersect, right? And now, if one of those, if only one of those intersects with the third line in the same point, and of course, the three intersect all in the same point, right? So that the only thing that we would have to compute would be the intersection point of those two lines. If that is same intersection point as of those two lines, we would be done, right? So let's imagine we compute the intersection point of those two lines. Right. But we won't do that because we already have the formula for lambda for any such two lines. Right? We just have to look at their respective ways of definition. We just have to look where they have corresponding constants. What constants we are talking about. For example, here we had AB. Here we have AD. Well, and the problem is I have here I took B as the point, here I took D as the point. So, but you see, you just have to look how you distributed the points among the lines, right? So, if we had LAB and we considered the intersection point with BD, then the points among the two lines we would distribute it as AB, BD, and now we have to look at the structure, how we did that. Well, for the first point, because this is the only thing that matters, for the first point, the a's do in the denominator, do the second in the numerator and the denominator, by which I mean B came first, A came second. That is, A came second. And we know if it is written first, then it is in the first line. Okay? Okay. Then B. And then here, of course, because it is related how it is defined, and of course, this comes first. All right. Then in BD, we had B coming second, coming first. And of course, there are some symmetries, AD same as DA. So the only thing that matters is how it looks this, how it looks here, how it looks here, right? And the thing was, here we had first two coordinates agree. Here we have second two coordinates agree. Okay, and that's already a bad news because, well, if we have second two coordinates agree, well, now we would have fun. So let's make same situation, make exactly same situation as here if we compare. Here we have first two coordinates agree, B, B. So for such lines, A, B, B, D, of course, they share one point, B, this point came first. Here, D, the point comes second. What do we have to do then to make the situation the same, completely symmetric to this situation? Of course, if we multiply the line by -1, nothing changes because they just uh, because we can take any lambda and we consider that whole set for lambdas. Of course, we can multiply by -1. So let's consider another form of LBD. That is the form multiplied by -1. And of course, we could call the constant the same, or we could call the constant differently. It doesn't matter. Oh, okay. I would not do that because I would have. Yes, yes, yes. I can do that. I can do that because this -1 wouldn't have any effect on this calculation in the second coordinate. So I can do that without any problems. So you see what I'm trying to do. I'm talking about such things because I don't want to compute that another time, but instead I want to look what played role of what in my calculations. And then I would know that the calculation would just go the same and I wouldn't have to do this calculation. I would have just to compare. Uh, if if the rows of D's and B's in the final expression actually the same here. So I wouldn't have to calculate, I would have just to compare. Right, and of course, as we would expect it would do, this just changes the row because we have to multiply with -1 everywhere. So minus p1 squared plus p2 squared minus p2 squared. And here 2d2 minus 2b2. Right, and lambda tilde is element R. And of course, I can now compute the intersection point for this new form. And I want also to have that in the new form so that the situation is completely symmetric, as I said, to the situation of the first two lines. Completely symmetric except for the first coordinate. But this gives again lambda tilde is given to lambda hat. So it didn't carry any information that is important for our calculation, for the shape of our calculation that it took by the first two lines and now will take by the second two lines. Okay. Two e2 minus 2u2 because we multiply by -1 minus okay, no, it doesn't work because by multiplying with -1 I would just reverse the sign either of that or of that. Oh, right. Then then it simply doesn't matter at all because this fraction is same fraction if I reverse the sign. So I don't even I don't even need uh, to make some -1 here. Okay. So I do the following thing. I just multiply here by -1, numerator by -1 in denominator. So yeah, it's much easier. Okay, so d1 squared minus b1 squared multiplied here plus what I wanted is achieved by much easier means when thinking about the line, right? I just multiply by -1 in the numerator and denominator, and it's actually exactly the same thing. Not in the sense of set, but even in the sense of numbers, what I obtained in. Right, d2 minus 2a2. Right, lambda hat. Yeah. Okay. That works, and we don't even need -1 because the numbers actually even stay the same. So it is achieved by even easier means, right? Okay. Well, now the situation is completely symmetric. Here we had that is the shared point. Here we had first coming this coordinate, first coordinate is the positive. Here D is the shared point. These coordinates are coming first. These coordinates are coming positive. Coordinates are coming first. These coordinates are coming positive, right? So, and now we can compare. And we can write down simply that expression for those second two lines because the calculation would have been exactly the same. It has to be because only the rows are important. The exact numbers, well, it was just situations you did those exact calculations, right? And now we would look which point would have played what role now. The role of the point B is played by the point D, right? So and now D is the shared point. D is coming first. So the role of the point B goes to D because D because that was the shared point. And in other two, it should be symmetric. We would expect it. So AB, other 2 points. AB are now D and A, and it doesn't matter what goes to what. We only have to be consistent because the rows were symmetric. So yeah, okay. And the expression should then be symmetric in D and A, and this is what we expect to see. And indeed, in the numerator list, here we have minus B2. Here we have minus, here we have D2, here we have minus A2, and here we have minus A, here we have minus D. Of course, norm and whatever, that is called Euclidean norm of that point, distance to 0, right? Norm squared, whatever. But I'm interested in the structure, and the structure is now marked by the letters. The rows are conveyed by the letters. And I'm claiming symmetry in D and A. That is, I could replace everywhere D small by A small, A big by D big, and vice versa. Okay, let's see if it works. Here we would have minus D2. Here we would have minus A, right? Minus D2, minus A here. All right. Mm, The problem is it doesn't work. It is not symmetric in A and D. It doesn't seem to be symmetric in that. Okay, that is absolutely weird. It has to. It has to be symmetric in A and D. But it is not. Wow. Wow. I have forgotten something, I'm sure. Oh, here we had minus, right? Here we had minus because we brought it from here. We had minus because we brought it from there. And this is exactly what happened. Right. But then it has to be symmetric. At least that is what I would expect. Ah, wait, the final expression is this. So, okay, it shouldn't change much, but let's look. Maybe we did a mistake there. I mean, there by comparison, because we were thrown off track by this B. But this expression looks much more symmetric, actually. If we replace that by D and that by A, we would have plus here. If we replace that by D and that by A, okay, no, we would not. This expression doesn't seem to be symmetric indeed. And that is very weird. That thing would give negative. I have fear and the feeling that would have to calculate that after all explicitly. Ah, no, it wouldn't help. Wouldn't help. But how come it's not symmetric? Okay, maybe I'm missing something. AB, BG, right. LAP, LBG. We have that, and we have that, and then we have that, and we have that. So, okay, was that symmetric to begin with? Of course it was. I mean, here we could have replaced A by D without problems. So why did it stop to work? We could have replaced everywhere A by D, no problem. So that is the final expression for lambda. Yes, of course the final expression should be symmetric. What am I talking about? Because here we could have replaced A by D and um, D by A without any problems. We would have gotten the same, right? So the problem is with our calculation. Okay, wow, that's enlightening. Or maybe the problem is not with our calculation, but I have to look at that and that simultaneously. Well, but at least it has to be symmetric as expected. And the question is, what went wrong? Here, of course, it's still symmetric because we can replace it anytime, right? Here, plus d2 minus c2. Here, it still works because we have d2, we have a2, we can replace. No problem with that. Where did it break? And why? It's not clear at all. I mean, we have that. Here again, we could have replaced everything. Like here we had, no. Here, for example, no. Here we could not. Here we could not. But here we could. Right, what changed? Here we could obviously, right? And here we could not anymore. Why? I mean, that doesn't make any sense. No, we could. Of course we could here. It's just that you have to be careful. A is replaced by D here. No, we could not. Well, but we should be able to. Okay. Well, plus a2 d1 plus a1 d2. Changing doesn't change anything, okay? Because we have just changed here ad, we have changed here ad, that doesn't have, nothing happens. Here minus d2 b1, here here plus a2 b1, right? Plus a2 b1. Here, if we changed, would be plus d2 b1 and plus d2 b1 plus d2 b1. But here is minus d2 b1. Okay, why does symmetry break here? That shouldn't happen like that. I mean, was it not symmetric to begin with? It was definitely. What I mean by symmetric, nothing would have changed if we would have replaced that with that, right? And now, for some reason, it seems to be not symmetric anymore. Oh no, I see. It is, but we have to take into account that thing, right? Because of course it has to be symmetric, but we have to take into account the whole of our expression. Okay, because we have deleted those, but we have deleted those on the other side too. Okay, we just can't keep a track of the symmetry anymore. But the symmetry is given here, and so it is given in this step. And if our calculation is correct, that the symmetry is given here, well, you can easily see that you can just exchange d by a and a by d in any place, and it stays same. Right? It says exactly same. The same will be written here. Right? And then the symmetry skips. And we arrive here. But now you're not interested in symmetry, but in how the calculation unfolds. And what we would get if the rows would be different. And we now know that, oh, that's the thing. Let's say we do same calculation. Then the row of A, okay, the row of B is certainly played by D. But the row of A is played by, oh, if we do same calculation, it doesn't matter. We just have, we could say that the row of A is played by A because we would have been just brought to this side, right? We have brought to this side. Here we had A2, 2, and we brought to this side. And here we bring to the side again. We've modified those fractions, right? Multiplied by -1 in denominator and numerator, already did it. And we brought to this side. So we bring here simply, so that this is brought to the side with A, we bring this to this side, right? And then the row of A is played by A. And the other thing is D. And now we'll look at that. And the row of B is played by D. That is what we have to exchange is B and D. Right, because the row of A is played by A. As we said, we bring it to that this side. And now let's make the magic happen. I hope that it will be exactly this, because if no, well, B2 minus D2. Okay, that's not that yet. If not, I think I'm done because it's just too much to compute. Of course, you could compute it all exactly and you would see that it works, but I won't do that. Just computers should do that, but I won't do that. All right, but let's replace it and hope for a miracle. B2, I mean, it should work, but it could be that it is not immediately seen. That's what I mean by miracle. Hope that it will be seen immediately. D2, oh, now B2, D22 minus A2. Minus A2. All right, A place same row. Minus A2. D, B2, G. 2. Right. Plus B2. So plus D2 here minus A2. D minus B, all right. And here plus D2. And here A minus B. Right, now here, A stays the same, B replaced by D. So 2 minus D1, B2 minus A1. So minus D1, B2 was right. Minus A1, D2 minus B2 plus B plus D2 B1 minus A2 D1 minus B1. I just replaced everywhere D by B and B by D. Right, and let's compare those two. Already wrong sign. Okay. But wait. We do not lose hope yet. This is a wrong sign. We know that. Minus E2, D22 minus B2 have same here, but with wrong sign. All right. We have that with wrong sign because in the brackets, pay attention, D minus B here, and here plus D2, A minus B. Plus D2, B minus A. Again, wrong sign. So if we multiply the numerator by minus, we get exactly this numerator as we liked, right? But now, pay attention to this here. What we get here is 2 multiplied by minus D1, B2, and that we find here with our sign. Minus A1, D2 minus B2. Minus A1, B2 minus D2. Wrong sign. Plus D2 B1 minus D2 B1. And here, minus A2 D1 minus B1. And here, minus A2 B1 minus D1. That is, if we multiply that by minus 1 and that by minus 1, we get that. That is, when we compute, and I explained to you that because of the shape of calculation, because only the shape of calculation determines how the calculation goes, it is exactly the result that we get for the lambda as the lambda characterizing the intersection point of these two lines. LBD and LAD. And this is exactly the lambda that characterizes this intersection point. And that is, this coordinate is equal to this. And this is exactly the lambda characterizing the intersection point of this. That is, this coordinate is equal to this. Yes, this coordinate is equal to this because this is same lambda. This is same lambda computed in that way, in the way of computing intersection point. So here we got the equalities of these lambdas, and then we have computed exactly the lambda that satisfies that the second coordinates are equal. And now we have first computed the lambda here. The lambda that satisfies that it is the lambda for which the point given by this lambda on this line and given by this lambda on this line is the same point. But now, same lambda does it for point on this line, same point on this line. And that is all three lambdas are equal. And the lambdas determine the points. And so this is point for this lambda, and this is for the same lambda, the same point that lies on here and on here. And this is for same lambda, point that lies on here, and point that lies on here. And that is the lines intersect in one point. Oh, God. You should think about it if you didn't catch that. You should also think why I didn't do the calculation. You could do the calculation, you would just come up with this result. If you don't believe me, do the calculation for these two lines exactly like I said, that you take the lines with same rows. So this would be the line with switched that here, which doesn't matter because we had just multiplied here by -1, and you bring to this line this, so that the A plays same row structurally, same shape of calculation, then you compute all this in that way, and you come up with this lambda. And that about that it really determines the same point of intersection with three lines. Well, you have to think about it. You could also compute that explicitly, that it is same point, or you could think why it works that way. It's actually rather trivial, but to explain it exactly, like, you have to see it. You just have to see it. Okay, so I didn't expect that it would be that kind of well, indeed, we have now computed the unique, because it would be necessarily unique. Even intersection point of two lines would be unique, but now such lambda exists, and is the unique, okay, the unique point of intersection of the three lines. Lines characterizing of the three lines characterizing equidistance from the respective pairs of given points. Respective pairs of the given 3 points A, B, C. And that characterizes equidistance. So it is intersection, and so it is this point is equidistant. The point of intersection is equidistant from one point and the other point, from one point and the other point, and from the third point and the first point. So it is equidistant from all 3 points with that. We have shown that there is a unique, and uniqueness is just that we now know that the circle necessarily would be characterized by those lines, and so by the intersection of lines, and such intersection is always unique if it exists. With that, we have shown that there is a unique circle through the points. We also derived, because you can just now take this formula for this lambda, and you can take formula for these lines, and you can just plug it into a computer, and this computer will calculate you the coordinates of that point explicitly. So we have also shown how to calculate the coordinates of the middle point of the circle, independent on the coordinates of those 3 points. We have also derived explicit construction of a middle point of a circle that is its coordinates independence of the given coordinates of the points ABC. And that's also great, right? That's also great. We derived an explicit construction for this middle point. And well, so we have shown, we have proved there is a unique circle because the circle is characterized by those lines. And we have proved there is such a circle. So we have proved if there is a circle, then it is unique because it is characterized by intersection of those lines necessarily because of the property of equidistance of all points on the circle. And the point which is equidistant from both should lie on the equidistance line of them. And then the middle point of a circle should lie on the intersection of at least two equidistant lines, but it is completely characterized by the intersection of the three equidistant lines. And we have shown the existence of such circle because we have shown that indeed such point does exist because there is an intersection point of such three lines. And I would like to finish this video by this short remark about collinear points. They also lie on a circle, but on a very special one. on very special circles. They lie on a circle. Remark. Um, look at circles with ever bigger radius. Now, not in connection to 3 points. Now it's just like, okay. So first, take this circle, radius 1, right? Then take circle of radius 2. And you know, it would be approximately that. That is circle of radius 2. All right. Then imagine, draw a very large circle that has to be really large. And now imagine we go very, very far and we draw very, very, very large circle. You see what is happening? That circle that we would have drawn then, it would look very, very much like a straight line. Like consider Earth. We don't even feel that the Earth is round if we are on it and are looking onto it without tools. It's like it's flat. And same is of course with one-dimensional object. If you have very, very large circle, then it is a line, or a circular line, then it is a line. And indeed, if we go with the radius to really infinity, then the circle becomes a line. And now here's the point. Take three collinear points. And of course, you know that the lines of equidistance it doesn't matter. Take a general case. lines of equidistance would be this line, would be this line, would be somewhere this line. They are just parallel, right? They're just parallel. There's nothing. They are parallel to this. They are orthogonal to this line. They are parallel themselves. But in an imaginary point, at infinity, and mathematically, you construct this point, you construct a certain type of space, and the Euclidean space, the Euclidean plane, is kind of part of a space. It can be seen as part of a space, and when those lines intersect, they are parallel. I have drawn that wrongly, but this point, this is at infinity. And if you now think of a circle, the circle middle point should lie at the intersection of the equidistance lines. This intersection would be infinity. So this circle is of infinite radius, and that completely fits to that. If you go like that to infinity, to infinity, to infinity, then someday or at some point, this circle becomes a line. A line is a circle with infinite radius, and so this coincided on a circle. And there is a generalization of objects like lines and circles. You call them general circles, and with that consideration, all 3 points, triples, all of them lie on a circle. And well, you can also think a little bit of what that space could look like. For example, oh well, it can be shown that the stereographic projection, that is a projection that makes maps on Earth, or it is one of the types of projections that makes maps of Earth. Maps all lines and all circles to the sphere so that they take the shape of circles. Stereographic projection. You know that just from lines of longitudes and lines of latitude, right? And then those points indeed would be mapped, points line on line. It would be mapped to a certain, of course that is now not linear, but somehow in a circle, to a circle that goes through the North Pole. So that space of which I talk, that it is kind of an imaginary space or something, well, kind of model of this space in a way is this sphere. Lysospheres are circles. And with that, I'd like to finish this. Well, maybe it's a little overkill for school level, I don't know. But well, I'm sure that some of you enjoyed that nonetheless, because well, there are people who really want to know how everything works. Okay, well, with that, we are done here. And you can now use the cool construction, so it wasn't for nothing. Okay, well, we are done.